Myself, Rahul Thakkar from LJ Institutes of Engineering and Technology. Now, in today's video, we are covering the topics such as derivation of equation of simple harmonic motion and free oscillation. So, let us start with the first topic of today's session, that is simple harmonic motion. So, let us first of all describe what is simple harmonic motion. It is also termed as SHM, simple harmonic motion. So, any motion which repeats itself at a regular interval according to a sinusoidal law is known as a simple harmonic motion, is known as a harmonic motion. The oscillation of simple pendulum or the motion of a mass m under a restoring force is an idealized model of an harmonic motion. In this case, the force is directly proportional to the displacement. The oscillatory motion in which the force is directly proportional to the displacement is known as the simple harmonic motion. So remember this definition. The oscillatory motion in which force is directly proportional to the displacement is known as a simple harmonic motion, and the motion must be repeating itself according to a sinusoidal law. Okay? Since the force is proportional to the displacement, the acceleration is not constant but varies with time. Simple harmonic motion is thus a non-uniformly accelerated motion. Hence, the equation of motion with constant acceleration are not applicable to the simple harmonic motions. Okay, whatever the equation of motion which we have studied under the chapters of acceleration and velocities, that were for the constant acceleration, but it is a non-uniform accelerated motion. So those equations which we studied earlier are not applicable in this case. Okay, in the 11th and 12th. So for that, consider a particle as shown in figure. Consider a particle moving along a circle of radius a with a constant speed of v as shown in figure. You can see it clearly over here. So draw a perpendicular from the point P on y dash and n be the projection of point P. The circle is known as a reference circle and the particle P is known as the reference particle. Now when the particle is at x, the projection is at O. When the particle moves from x to y, the projection moves from O to y dash, as you can see in the figure. So when the particle reaches x dash, the projection comes back to the y dash to O. So when the particle reaches y, the projection also reaches y, and when the particle comes to the x, the projection comes back to the O. Thus a particle moves along the reference circle, the projection moves along the diameter y and y dash. Now if in a plane of projection we have a particle to move, as the projection moves under the influence of some force, the particle will be said to performing a linear simple harmonic motion along y o y dash, as you can see in the figure. So what are the conditions for the occurrence of simple harmonic motion? So in case of mechanical oscillations, three conditions must be satisfied for the occurrence of simple harmonic motion. So there must be a position of stable equilibrium, there must be no dissipation of energy, and the acceleration should be proportional to the displacement and opposite in direction. The acceleration must be proportional to the displacement in order to follow the simple harmonic motion, and it must be in the opposite direction. So moving further, let us consider a block of mass m attached to the spring as shown in figure. You can see it over here. A block of mass m is attached to a spring, and for three different cases it is shown. Okay, so when the mass is pulled left to it, it oscillates about the equilibrium position, and the direct distance of the mass from its equilibrium position is known as a displacement. The restoring force acting on a body is due to the stiffness of the spring and is given by the Hooke's law. You all are aware about the Hooke's law. F is equals to minus kx, that is the equation. Okay, where x is the displacement of the spring from the equilibrium position and k is known as the elastic constant, which represents the force required to displace the mass for 1 unit distance. Okay, where K is known as the elastic constant or it is known as the stiffness of the spring. Okay. The negative sign in the expression indicates that the force is opposite to the displacement. When the mass is pulled to the right, the spring gets stretched. Then X is positive and the force is negative and is directed to the left. When X is negative, the spring is compressed and F is positive and directed to the right. So according to Newton's second law of motion, the restoring force produced acceleration. So thus we know that F is equals to minus Kx is equals to m into a, mass into acceleration. So we can say that restoring force is equals to the inertial force. So on placing the values of acceleration as d square x by dt square, we get m into d square x by dt square is equals to minus kx. On rearranging the equation, we get d square x by dt square plus k by m into x is equals to 0. This equation is merely another way of writing Newton's second law and is known as a differential equation of simple harmonic motion. If we put k by m is equals to omega square in the above equation, we have d square x by dt square plus omega square into x is equals to 0, where omega is known as the angular frequency and is given by omega is equals to under root k by m. Also, the time period of oscillation is given by the time period of the mass is independent of the amplitude. So for a given elastic constant, the period increases with the increase in the mass of the block. A heavier mass oscillates more slowly for a given mass and the period decreases as K increases. A stiffer spring causes quicker oscillations. All simple harmonic motion obeys the differential equation of the equation discussed above. Okay. Now coming to the next topic, that is free oscillations. So free oscillations are the oscillations that appears in a system as the result of a single initial deviation of a system from its state of equilibrium. When a pendulum is displaced from its equilibrium position and left to the action of internal forces, it undergoes free oscillation with a frequency given by V is equals to 1 upon 2 pi under root G by L. The time period and the frequency of simple pendulum depends only on the length of the string and the acceleration due to the gravity and is independent of the mass. The frequency will be the same as long as the pendulum does not experience a resistance to its motion. The frequency with which the pendulum oscillates freely at its own is known as a natural frequency. Thus, if no resistance is offered to the motion of any oscillating body by air friction or other forces, the body will keep on oscillating indefinitely as its natural frequency is shown in figure. Such an oscillation is known as an ideal oscillator. The period of oscillation of an ideal oscillator is independent of amplitude and a characteristic property of oscillation. The ideal system are frictionless and the energy is not dissipated away and hence the total mechanical energy and the amplitude remains constant. Let us take one example to understand simple harmonic motion. Okay? Consider a body of mass m is equals to 4.9 kg hangs from a spring and oscillates with a period of 0.6 second. Consider a body which is hanging from a spring and it oscillates at a period of 0.6 second. How much will the spring shorten when the body is removed? So over here the given data is provided, only two data, that is time is given and the mass is given. So time is equals to 0.6 second and mass is equals to 4.9 kilogram is given. So now let us take a look on this solution. So we know that the equation T is equals to 2 pi under root m by k, which we have derived it earlier. T is equals to 2 pi under root m by k. So placing the values of m and 0.6 as T, we can get K is equals to 536.8 Newton upon meter. That is the stiffness. Now, how much the spring will shorten? We need to find out that. So, K is known as a stiffness, that is force per unit length. So, we can place K is equals to F by X. And also we have F is equals to M into G, mass into gravitational acceleration. So that is M into G by X. On placing the value, we can get X is equals to 8.9 centimeters. That's it for today, guys. Thanks for watching.